Hello and welcome everyone to our Lunch and Learn session about graph embeddings with AQL. I am Sachin Sharma. I am a graph machine learning research engineer at Arango Database. Today I am excited to share my knowledge of the concepts regarding graph embeddings with AQL. Fantastic crops and where to find them. So according to Gartner's top 10 data and analytics trends for 2021, as many as 50% of Gartner's client inquiries around the topic of AI involving a discussion around the use of graph technology. Starting with an important question, why graphs are fantastic? We can answer this question in a few parts. First, one of the things which make the graph fascinating is their ability to connect isolated data points in space, which is, however, missing in another forms of data representations like 2D grid structures, which are used to represent image pixels, 1D sequences used for text, speech, or time series. The second important aspect of graph is that it allows us to store relational knowledge among interacting entities. That is how different sets of entities are related to each other based on some measure. So representations like 2D grid structures or 1D sequences accept the graph lie in Euclidean space, that is regular unstructured data, and the well-known method to extract meaningful patterns from the data in the Euclidean domain is convolutional neural networks. However, in the real world, we are also surrounded by graph data, for example, Internet of Things, 3D point clouds, social network, event graphs, chemical molecules, where nodes represent real-world entities and edges are associated with the relationships between those entities. So these are the typical tasks in graph machine learning. Graphs as a unique non-Euclidean data structure cannot be operated by CNNs and require a special method to handle its non-regular structures, which has recently led to the progress in the area of graph neural networks. In machine learning universe, graph data structures are exploited by the graph neural networks to perform the task of node classification, link prediction, graph classification, and graph clustering. Now, what is a graph? So this is just a formal definition of a graph. So the graph is a data structure made up of nodes or vertices and edges. Edge describes a relationship between two node entities based on some measure. It is mathematically defined as G of V, uh, capital G, and then V as a set of capital V as a set of vertices and capital E as a set of edges inside the graph. So traditional machine learning on graphs follows a standard machine learning pipeline to extract structural information from graphs. We start with extracting some important graph statistics or features from a given graph. For example, node degrees or clustering coefficient. Once these features are extracted manually, we can use them as an input to the machine learning classifier, example SVM or logistic regression. So on the slide, we can see the node degree features extracted from the given graph and we use it as an input to our machine learning classifier. So this is how the traditional machine learning on graph was done. But there are some caveats of applying these traditional method. Uh, that is, the approach is restricted because these hand-engineered features are inflexible. That is, they cannot adapt during the learning process, and designing these features can be time-consuming and it could be an expensive process. So now there's come the another question that can we apply convolutional operations on graphs? So convolutional neural networks are designed to operate on regular fixed sized data structures, or you can say that the data structures which can be represented in Euclidean space. Let's understand the term regularity in data structure with the help of this cat image. Images can be seen as a special type of graph known as the grid graph. Now, applying convolution in this case means that we examine the neighbors of each pixel by aggregating their values. For example, this red pixel where we aggregate the values around it. One thing to note here is that each pixel in the 2D grid is surrounded by a fixed number of neighbors. So if we move this window from left to right or top to bottom, the neighborhood size of a target pixel remains the same. However, in graphs, the neighborhood size of a target node varies. For example, in social network graphs like Facebook, a popular person could have millions of connections or neighbors, whereas the normal one can have very few connections. Also, in the 2D grid, there is a fixed ordering of neighbors, whereas in the graphs, the order of the neighborhood of a target node is arbitrary, and this property is also known as permutation invariant. So, graph convolutions, or also known as message passing neural networks. So, in the graph convolutional networks, the convolutional like operation is represented as a two-step process, that is aggregate and update. We aggregate the features from the neighborhood of a node and then update the target node features with these aggregated features. As we have seen, the limitation of applying traditional machine learning on graphs is that the hand engineered features are inflexible. The next question that comes into our mind is finding a way to integrate the information about graph structure. Example, information about the node's global position in the graph or its local neighborhood structure. And we want to embed this information into a machine learning model. Therefore, to tackle this problem, representation learning approaches have been adopted to encode the structural information about the graphs into the Euclidean space, or also known as the vector or embedding space. The key idea behind graph representation learning is to learn a mapping function that embed nodes or entire graphs or subgraphs from non-Euclidean space as a points in a low dimensional vector space. So the aim here is to optimize this mapping so that the nodes that are nearby in the original network should also remain very close to each other in the embedding space while pushing unconnected nodes apart. Therefore, by doing this, we can preserve the geometric relationship of the original network inside the embedding space by learning a mapping function. The two key components here are: the first one is an encoder which maps a node to low dimensional vector. And the second is the similarity function, which defines how relationships in the input network map to relationships in the embedding space. Here, the similarity function could be, for example, cosine or Euclidean distance, depending upon his or her choice. Let's understand this more intuitively with an interesting example from the graph structure of the Zachary Karate Club social network. In this graph, the node represents the persons and their existence between two persons if they are friends. So the coloring in the graph represent different communities. The figure A represents the Zachary Karate Club social network, and the B illustrates the 2D visualization of node embeddings created from the karate graph using a deep walk method, which is one of the graph representation learning method. So if you analyze both the diagrams, you will find that the mapping of nodes from a graph structure to an embedding space, which is a figure B, is learned in such a manner or is performed in such a manner that the distances between the nodes in the embedding space mirror closeness in the original graph, that is preserving the structure of the node's neighborhood. For example, the community of the people marked as violet and green shares close proximity in the 2D space, as compared to the communities violet and sea green, which are very far away from each other, which is similar to what there is in the karate graph. So once we have these learned node embeddings, we can use them for various machine learning downstream tasks, can be used as a feature input for downstream machine learning tasks, example, community detection via node classification or link prediction. We could construct a KNN or cosine similarity graph from embeddings. The graph could be used to make recommendations, example, product recommendations, visual exploration of data by reducing them to 2 or 3 dimensions using UMAP or Tesney algorithms, dataset comparisons, and transfer learning. This slide shows the embedding visualization of the Amazon product recommendation dataset at 3 different layers of graph stage. In this graph dataset, the node represents the Amazon product description, and edges between the two products indicate products purchased together. So if you see the layer 1 embeddings, they show that the model is not able to separate the product categories well, as the embeddings of different product categories are very close together. Therefore, we cannot predict or estimate with a high probability which two products can be bought together in the future, or if someone buys one product, then which other product he or she also might be interested. At layer 2, we can see some separate clusters of product categories forming, and we can draw some valuable insights from them. For example, cluster C1, we are having here movies and TV versus CDs and vinyl. The second cluster in which we are having this grocery and government food versus health and personal care. And the third cluster is the video games versus toys and games. And at the end, at the layer 3, representations are little finer than the layer second. We can see some more distant clusters. And then again, there are cluster C1 with cell phones and accessories versus electronics, movies and TVs versus CDs and vinyl, and as in and same as in layer 2, which is same as in layer 2, and then the last cluster C3, which is beauty versus health and personal care products. So if anyone wonders how I created these visualizations of node embeddings, then I have already prepared a Google Colab notebook with which you can play around. And so these are the links to this notebook. So now we will move to our hands-on part, where we are going to perform a graph embeddings with the help of AQL. So this is the notebook which I have prepared for you guys. So here the idea is that we are going to use the Amazon product graph embeddings, which are generated using the graph sage and RangoDB's AQL query language to perform recommendations. So in order to know how these embeddings are generated, please go through this repository and you will find some and you will find out that how one can train a graph sage model, and afterwards uh, how the embeddings at different layers can be generated, and afterwards and then at the end how we can store these embeddings inside the Arango database. So here I'm assuming that my embeddings are already stored inside my database. So what we are going to do is that we are going to import this Arango client, which is going to help us to connect to the database. So we here in the next cell, we are connecting to a database, and yeah, these are some yeah, client connections which we are making. And then yeah, now let's say so for the demo purposes, I have picked up some random product IDs. So the goal here is to given a product ID or given a product, the goal is to find a similar products which can be bought together with this product. So if I run this cell, what I'm going to get is the embeddings of this product at the last layer, which I had stored inside my database. So these is the 47 dimensional embedding vector, which I got it from trained graphs edge model. And so this is the product category to which this product belongs to. So this product belongs to home and kitchen class. And then the then what we are going to do is that we are going to find out the similar products based on this query product. So here is the AQL query, which we are going to run to find out the similar products. So when I'll come in just a second about explaining this query. So when I run this query, what I found is that let's see the similar products. So yeah, so let's see like how I'm calculating the similar products. So here we are using this cosine similarity to retrieve the products which can be bought together with the query product. So the cosine similarity is calculated between the node embeddings of a query product, which is which is this product, and all the other 4,999 products. So this is the formula for calculating the cosine similarity between the two products. Uh, and then once we calculate the cosine similarity, we can then sort the products and return the highly likely bought together products with the query product. So basically what I did is that I just implemented this formula into this AQL query. And then afterwards so this is the where I'm calculating the cosine similarity between this query product and all the other products. And afterwards, I'm just sorting sorting these products according to the high cosine similarity, which basically return us the most similar products which can be bought together. So let's see the output here. So for example, with our query product was home and kitchen. So let's see what is the product which can be bought together with the highest cosine similarity score. So this one is the tools and home improvement with a cosine similarity score of 98%. We can see that this is making sense because if you go to a market and buy a home and kitchen products, then there is lot of chance that you might also buy the products uh, which are uh, related to tools and home improvement. And let's see if we can find the second highest similar product. Okay, so it's the baby products. So then again, it's the second highest similar product is also making sense. So with the home and kitchen products, you want to buy a baby product as well. So um, which is making sense. And the third highest similar product, uh, patio, lawn, and garden is also a kind of relevant bought together product with home and kitchen. So yeah, we can see that the results are making sense. And yeah, so with this, I hope everyone enjoyed this very quick lunch and learn session about quick introduction to graph embeddings with AQL query language. If you are having any kind of doubt or any kind of question, just please reach out to me. Thank you very much and enjoy your day.